So remember, coming up, we have a midterm a week from today. And if you want to see what its format's going to look like, go to the exams link. And we have a sample midterm there from last semester. And this one will be very similar. So there will be a number of multiple choice and multiple answer questions that test your basic knowledge of the material. And then there will be some problems that test your ability to form SQL queries, that test your ability to write or draw entity relationship diagrams, and ones that test your ability to manipulate either B+Trees or extendable hash tables. So those are what you can expect to see. And then the graduate students will probably have one or two additional questions on the exam for them that they'll need to fill out. And you can see last time it was a relational calculus problem that just graduate students did. And they also did another SQL problem. So there'll probably be a couple extra questions for the graduate students. So I encourage you to take a look at this exam and the solutions that were for it, and that gives you a good idea of what to expect. If you're thinking about how to study for the exam, it's a good idea to look at the quizzes, because a lot of the multiple choice questions in the past have been pulled from the quizzes. So take a look at those. And of course, look at your homework assignments. Make sure that you understand anything that look at the solutions. Make sure that if there's a difference between the solutions and your answers, you understand what happened. One of the biggest reasons people lose points on the exam is the ER diagram, so it's important that you make sure that you are on my page, same wavelength with it. And on Thursday, I'm going to have a review session. So you'll see that if you look at the lecture notes for this coming Thursday, it says catch-up day, but it may be that I don't quite get through extendable hashing all the way today. If I don't, I'll finish that up on Thursday, but otherwise I plan to devote Thursday to a review session for the exam. And I found that this really helped last semester in 365. It seemed like exam scores went up because of that. So I highly encourage you to come on Thursday as we go over stuff. So questions about that? Anyone? Yes?
Did you say this last bit of stuff, like the extendable hashing, is that on?
Yes. So it will be. Everything up to today's lecture will be on the exam. And you'll also note that on the homework assignments that this particular one is due a hard deadline of 6 a.m. on Friday. It's not no late acceptances, and the reason is so I can get those homework solutions out to you so you can check and see if what the right answers really were. Other questions? Yes, Luke.
I couldn't find appendix F in the book. It goes up to E.
So they used to have a online appendix, but it doesn't really matter because I actually think that that appendix F covers the same material that my handouts cover that's on Canvas. Oops. I know it says Blackboard, but it's on Canvas. If you look, you'll see that there's a extendable hashing and B+Tree notes. And actually, I think that's from a book we used to use in 140 and 302, and I always liked that book. I think it's much better than Appendix F anyhow. So, yeah, I seem to remember that at some point they put Appendix F on the web.
Because they reference it in the book, and it only goes up to E.
I gotcha. Yep, that's kind of annoying. It's other questions. Okay, so in that case, this is the last lecture on databases. After next Tuesday, we will be starting into scripting languages. And last Tuesday, we were talking about indexing and how you decide which attributes of relations to place indices on. And we briefly also talked about the different file organizations that you could choose for your relations. It was a heap, which was an unordered file, a B+Tree, or an extendable hash table. And if you remember, we said that you use B+Trees when you want something called range queries. So you want things clustered physically next to each other, and you use B+Trees for range queries. Things like, I want all 5K race results for people who finished between 16 and 17 minutes. Or I want all people whose salary is between $5,000 and $10,000. So you would want to physically cluster all those records together. And I also said that it's frequently the case that the file is not clustered on the primary key. Does anyone remember why we don't typically cluster on the primary key? Very good. So the primary key is an artificial key. It's not a natural key, and therefore you don't tend to have range queries on a artificial key. It makes no sense because artificial keys tend to be randomly generated. So you really want the cluster to be on an attribute that you would expect a range query to be executed on, like salary or times in a race. Now, I also mentioned that sometimes it's clustered on last name because that's a common attribute, and it's less likely to have a range query on last name. But that's another common attribute used for clustering. And then extendable hashing is typically used for the secondary indices. And the reason for that is that you can't cluster on more than one attribute. So the remaining ones have to be treated more like point queries. And point queries are best executed using hash tables. They have better performance than B+Trees. Okay, so where we stopped was I was trying to motivate why you needed to extend B+Trees or binary search trees. That binary search trees don't work well in secondary storage. And the example I gave was you have, say, 10 million records for the driver's licenses. And so you end up with an enormous, even if it's a balanced binary search tree, the number of levels is going to be roughly 25 for 10 million records. And the problem with that is that each level requires a disk access when you access the node. And disk accesses, as we discussed last time, are expensive relative to CPU time. You can execute hundreds of thousands. In fact, at this point, you can probably execute millions of instructions in the interval that it takes to execute one disk access. So having 25 disk accesses for a 10 million record file is unacceptable. It just takes way too long. If you remember, I said that you might get about 200 disk accesses a second. That's not very good relative, again, to CPU. Here, even if you had a fully devoted disk system, which is unlikely that you do, other people are also probably using the database, it would still take 1/8 of a second just to get those disk blocks into memory and to process them. So we have to come up with a way that minimizes disk accesses, and the idea for binary search trees is simple. You simply increase the branching factor. And by increasing the branching factor, you decrease the depth of the tree. And because you still are only going to access one node at each level, if you say only have now 4 levels rather than 25, you'll reduce the number of disk accesses to at most 4. And typically, you can keep at least the top level, which is just a single node in memory, and often you can keep parts of the second level in memory too, in which case you'll have even fewer disk accesses. So there's sophisticated caching strategies that keep frequently used what we call directory or index blocks in memory, and that can further reduce the number of disk accesses that you need. But we're not going to talk about those disk caching strategies. When I ask on an exam, what is the maximum number of disk accesses for something, I assume that everything is on disk, that nothing is cached, and I want the worst case answer. So a B+ tree is a tree where you store, so a B+ tree is going to be a tree that has multiple children, so up to M children, and stores keys, stores only keys in interior nodes. Okay, and then in the leaf stores tuples in leaf nodes. Now, the leaf nodes are actually going to be the blocks for, if this is a clustered, if you have a clustered file, then what your leaf nodes are really the blocks containing the tuples, and you're just pointing to them. So you actually may, well, sorry, that was bad. That's going to be an extendable hash table that does that. So B+Trees, tuples are stored in the leaf nodes. And for leaf nodes, so leaf nodes can store L divided by 2 to L tuples. And interior nodes can store M divided by 2 to M keys. And if you're wondering what this symbol right here is, this upper bound. So for example, if L is 5, 5 divided by 2 is 2.5. That rounds it up to the nearest integer, so that would be 3. So we impose a restriction that the leaf nodes must be at least half full and the interior nodes must be half full. So logically what this is saying is all nodes must be at least half full. So that's an important half. Yep, not full. Must be at least half full. So that's going to be important for ensuring that the tree doesn't get to be really deep. It ensures that it will be bushy. Now there's one exception, and that is the root node. So the root node is the only exception. Root node may have 2 to M children. It's the only exception. You typically would not have a B+ tree where the root is actually the only node and therefore contains records, because why bother indexing in that case? So I guess you can make an argument when you first start inserting, you might have to do it. So I guess technically a root node may have 2 to M children, or if there is only one block or only one child, then the root contains, or the root is the child. That is, in the special case where you only have one block for the entire relation, then the root node would be that block. And the only reason really to put that in there is if you were writing the algorithm, initially when you do your first set of L divide or L insertions, are all going to go into one block. So that's the only reason I put it there. It's an implementation detail. For those of you who are in Dr. Planck's 594 or 494, you're probably dealing with these issues. So really, for this course, all you really are going to be responsible for is the root node may have 2 to m children. It's the only node allowed to be less than half full. Okay, so these are the rules of the game. But that's fine. That's the rules of the game. What are we really talking about? So I'm going to actually, for that, go to here. So here is a sample B, and one thing I need to warn you about is the handout talks about B-trees, and everyone else, their definition of a B-tree is what everyone else calls a B+ tree. Okay, I should be clear about that. We're talking about B+ trees here. There is also a notion of a B tree. Okay, a B tree allows records to be stored at interior nodes. B+ trees only allow keys to be stored in the interior nodes and store all the records at the leaf nodes. So in this course, what we are talking about is B+ trees. And the handout uses unconventional terminology because while the handout is describing what is conventionally called a B+ tree, it's referring to it as a B tree. That is not the typical definition of a B tree. Okay, so we need to be really clear about that because one semester it caused a lot of confusion in here. Okay, so I know that this diagram is only in effect showing keys, but the leaf nodes would really be storing the entire record. Okay, so what happens in a B+ tree is it's a lot like a binary search tree. If you have a key, then everything in the left child is less than that key. So if you look to the left of 41, you'll see that everything in its left subtree is less than 41. And you'll see that everything in its right, so-called right subtree, is greater than 41. So in a B+ tree, it's very similar to a binary search tree in that with each key in effect has a left child and a right child, except that in each node there can be multiple keys. And so what you do if you're searching for a key in a B+ tree, let's just work through an example. Let's say we want to find 81. Okay, so what we're going to do is start at the root, and we're going to keep going until we find so the search strategy is to keep going until we find a key that is greater than our search key. So search a node until a key is greater than the search key. Okay, yes. Okay. So you'll notice that, so let's start with 81. So we're going to search through here until we come to a key that's greater than 81, and that's 87. When we do that, we move to the left child. So then search a node until a key is greater. Okay, descend to the left child unless you've exhausted the keys, meaning you're greater than any key, in which case you descend to the right child. Okay, so if I had a key that was 87 or greater, then that's the only time I would descend to the right child. In every other case, I descend to the left child. But if I go through all the keys in the node and none of them are greater than my search key, then I will descend ultimately to the right child. So that's the only exception. But in this case, we do come to a key greater than 81, which is 87. So we descend to the left child, which is right there. And again, we search now through this node. And 83 is greater than 81. So again, we descend. And now we're at a leaf node. So we simply search through the tuples, and it's either there or it's not there. Okay? So you may be wondering, okay, so any questions about that? Okay, so very much, yes.
So if this is a B+ tree,
Mm-hmm.
those are not values that are being stored in the tree?
Correct, they're just keys. So in the interior nodes, it's just keys. In the leaves, which is what these things are, you would be storing the entire tuple.
So
Now for
anyways,
brevity, the author is only showing you keys everywhere. Okay, so the authors, otherwise he wouldn't be able to really, everything would be too tiny. So the leaf nodes, here the author's only showing keys, but in reality, leaf nodes would contain the entire tuple. Yes?
So just on a technical point, so when they're storing the whole tuple,
Mm-hmm.
when you're using a variable size data structure like varchar, do they just assume a large value for figuring out how many things they can hold?
That's a good question. One that I've never thought of. So I am not sure. Rather than trying to wing it,
Yeah.
I would have to look it up. I think these are all assuming fixed size records. So my guess, and I will take a guess at it, is that you would have, in effect, the leaf nodes also be just storing keys, and they would point off to the blocks, but I cannot be positive about it.
Yeah.
That seems like an interesting question, and I don't have a good answer. Okay. Other questions? Yes. These would typically, this is for a B+ trace, this is typically going to be the cluster key, the cluster attribute. Okay. So the records are being physically stored together if their keys are close to one another. Other questions? Okay, so let's say now we were searching for a key that's actually going to match something. So let's instead search for 87. So in this case, what happens, actually let's search for 66 to show what happens. So we search for 66, and actually let's clear everything. That's not what I want. Okay, so let's say that now we're searching for 66. So same thing, we're going to keep searching. When we get to 66, that key is not greater than our search key, so we continue to 87. So 66 is not less than 66, so we continue. And we end up finding that 66 is less than 87, so we actually go here. And again, when we come down to this one, 66 is less than 72, and you see that it is the first record in the right subtree for 66. So when the search key is equal to a key in the node, then if the record exists for that key, it will be in the right subtree, at least for this course. Okay, so if I have on an exam, that's how it needs to be. Now, searching is easy. The hard part is inserting and deleting. It's actually not so hard even to describe it. It's hard to implement it, as those of you in 494 and 594 know. So the implementation is also easy if there's a space in the leaf. So let's say, as the book says, which are they going to say? So they want to insert 57 into this B plus tree. So we're inserting 57. So same search strategy. We need to find the leaf node that should contain it. So 57 is less than 66. So we go here, and based on what I've told you, which child is going to contain 57? The rightmost one. So when we go through, none of the keys, the biggest key is still not greater than the search key, so we're going to end up descending to the last leaf. Now, in order to know whether we can insert a tuple into this block or not, we need to know what L is. Remember, L is the maximum number of tuples per leaf, and here L is equal to 5. And you can tell by the number of branches here that M is also equal to 5 in this case. Now that's rare. Usually M is much, much greater than L. Can someone tell me why M is usually much, much greater than L?
Because you can store a lot more just keys in a block.
Very good. Because you can store a lot more just keys than you can tuples. Because the blocks are the same size. Let's say the blocks were the standard 4096 bytes. Let's say the keys were 4 bytes and the tuples are 100 bytes. Okay, so it should be pretty clear that L is 40. Okay, M is a little less clear. It's not 4096 divided by 4. Why? Why can't I just pack 1024 keys into a block if the keys are 4 bytes? The pointers take up memory. So it all depends on how many bytes you need for each pointer. Because if you have M children, you have how many keys? Very good, except I always make that mistake too. If you have M children, you actually only need M minus 1 keys. I make the same mistake, that's why so if you have M children, you only need M minus 1 keys. So it's actually, in this case, 4 times M minus 1 plus M times whatever the size of the pointer is. Let's just say for grins, it's 4. So it would be this equation, and you would end up with 8M minus 4 equals 4096. 8M equals 5000. and that's something like 625. So I think M in this case is equal to 625. Okay, that's a lot bigger than 40. So in this case, M would be equal to 625 and L would be equal to 40. That's a pretty huge branching factor, right? That's going to really, for 10 million records, that's going to really drive down the depth level, and we'll talk about that in a bit. But in general, I just want you to know M is much, much greater than L, and that's because in a B+ tree, we're only storing keys in the interior nodes. But for book purposes, we have to keep in, for test purposes, generally L and M are going to be pretty close because we can't have these enormous branching factors. Okay, so we're assuming that L is 5 and M is 5. So coming back to our example, we were inserting 57. So in this case, can we insert 57 into this block? Yes, there's room for it. So 57 would go right there. So that's the easy case where there is enough room in the leaf for the tuple. Okay? So when we're done with that, 57, here it is. Okay? But now we're going to insert 55. So if we insert 55, we're going to end up also down here. And now there's no longer room because we're only allowed to have 5 tuples in a leaf, and this one wants to have 6. So what we do in this case is we split the leaf in half, or into 2 blocks, and we move half the records into one block and half into the other. This is important. For this course, if L is odd, okay, move the extra tuple into the left block. That's only for this course. It can go either way, but for this course, so that we're all on the same page on homework assignments and for exams. So if L is even, that was wrong. If L is even. Okay, here it's okay. With L equal 5, there's going to be 6 tuples. We can evenly divide them. But if L was 4, then the 5th tuple would cause the split, and now there's an extra tuple. 3 go in one, 2 go in the other. Please put the extra tuple in the left block, okay? We good? You wrote that down because that's important for homework and exams. Okay, so in this case what happens is that we'll have one block that has 54, 55, and 56 in it, and the second block is going to have 57, 58, and 59. And notice we only have to allocate one new block. We don't have to allocate 2 new blocks. Okay? So we are moving half of the tuples into the new block. But now we also are going to have to add a key to the parent to point to the new block. So what key do you think gets added here? 57, very good. It's you add the smallest key in the right block. So add the smallest key in the right block to the parent. So in that case, you had 57. So pretty easy, 57 points here and 54 points here. So that was also a fairly simple case. Any questions about that case?
By
Yes.
extra
Well,
tuple,
well-
do you mean?
Well, just a sec. There was a question down here first.
Why would we not just move to 54 to the left and update?
Very good question. So the question is, instead of this splitting strategy, why don't we just move 54 down? Why don't we just, instead of this splitting strategy, why don't we just take 54, move it to here, and then we'll have room? And the answer is that I believe in real systems, that tends to be the optimization that's done. But don't do it in this class. Okay, if you do it in this class and people always do it on the exams, you'll lose some points. Okay, so that's the other option, is to move, is to see if the neighbor can hold the extra key, and if it can, move a tuple there, and that way we don't have to split the node and it makes the tree fuller. Okay, so I don't actually implement B+Trees for a living. I suspect that and the book notes that. It says that if you look, I'm sorry, not the book, the handout notes that strategy. But the thing is, if the neighbor was also full, you would have to split. Okay, so in this course, we're just going to assume if the node gets full, you got to split it. Don't move it off to a neighbor. Okay. But in real world, I think a lot of implementations actually check the neighbor, both neighbors. And if either one has room, they actually move them around. Now, there is an issue with that, which is that requires more disk accesses, because you have to check both neighbors, and that, so you may end up doing reads. It makes it more complicated. But nonetheless, your idea is the one I think is used in practice. Okay, other questions? There was another question from the back.
Yeah, by extra tuple, you mean the one that you're inserting?
Yes. Well, no, because you're going to insert the tuple into its lexicographic order. So it's the extra tuple is if you just have A, B, C, D, E. Okay, you're going to move the top three to the left and the bottom two to the right. So it's the extra tuple goes somewhere. It could go at the end. It could go in the middle. It could go at the beginning. Yes.
If you were to move 54 over to the left tuple,
Mm-hmm.
would the key in the interior mode get updated?
Yes. Mm-hmm. So that's what I mean by there is it makes it fuller, but you also have more disk accesses going on. So it's and like I said, actually, the more I think about it, the less certain I am that that's done in practice because of the extra disk accesses. So that's a possible strategy. Don't use it. Okay? It always turns an interesting problem into a trivial one, which makes me irritable when I see it on an exam and causes you to get almost no points for your solution. Okay? So, other questions? Okay, so now 57 is in this tree, and we have, this is the resulting tree, so they've updated it. 57's now there, and they point to the two children. Now, they end up inserting something more. So they're going to split two leaves. So now they're going to insert 40, I believe. Yes. So now let's insert 40. Okay, so we go 40 to here, then down to here. You can see there's not enough room, so we're going to have to split into two. 35, 36, 37, here, 38, 39, and 40. And which key comes up to the parent? 38. problem is that we can only store m minus 1. So if we have m children, we can only store m minus 1 keys. So m is 5. We can only store 4 keys. So we can't store that 5th key. It is full. So now we're going to have to split this node right here. Now it's different. Now what we do is we promote the middle key to the parent. And it physically leaves, so 26 leaves the split node, interior node, and moves to the parent. That's different than the leaf because you have to store the tuple no matter what in the leaf. So when you split a leaf, you also promote that key to the parent. It kind of looks like a duplicate. But if you split an interior node, the key physically leaves the split node and moves up to the parent. So 26 moves up to the parent, and what you're left with is 2 nodes, 8 and 18, and the second node containing 35 and 38. Okay, and if you look at the result, so now here 26's left child is 8 and 18, its right child is 35 and 38, and you can see that there were going to be, before, there were 5 leaves associated with that parent. When we split the node, we got 6. So half the children are now pointed to by this node, and half are pointed to by that node. Okay? So that's a case where you have to split multiple interior nodes, and in that case, during the splits, the middle key gets promoted. Okay? Now, again for this course, this was very handy because in this case, m was odd, and it just so happened that the number of keys in each of the 2 resulting nodes were the same. But what if m was even? We're going to have the same issue. There's going to be 6 keys now, A, B, C, D, E, F. And the question is, which key gets promoted? Because which keys could we promote in this case? C or D. So again, I need to lay down a rule for this course. In the real world, it doesn't matter which you choose as long as you're consistent. In this case, if m is odd, in this course, if m is even, then promote the leftmost of the 2 middle keys. Okay, so that means in my example, promote C because it's the leftmost. Okay, again, real world, either way is fine, but this course, my homeworks, you're promoting, or exams, if m is even, you're going to promote the leftmost of the 2 middle keys. Okay. So we have one more interesting case to consider, and that's going to require filling up this tree, but eventually we want to show you what happens if the root needs to split. Okay, that's going to take a lot of insertions right here because, as you can see, there's a lot of emptiness here. And the way I think they're going to do it is they're going to start filling up this particular tree. So they do a bunch of insertions. Wait a minute. Come on, where did they do our split? Oh, they didn't do a root split. Wow, okay. Well, we need to do a root split. Did they really not do a root split? They really did not do a root split. Okay. So let's put 47 in here. And now let's try to add 43. Okay, so 43 is less than 66, so we go down here. 43 is less than 48, so we go down here. And there's not enough room, so we have to split. We're going to have 41, 42, and 43. And over in the other one, we're going to have 44, 46, 47. So we're going to try to promote 44 up to here. But that's full, so we need to split and promote 51 up to here, giving us 26, 41, 51, 66, and 87. Okay, but that's full, so we promote, and again we promote the middle one, so 51 is going to become a new root, increasing the level of the tree by 1, and we'll now have something that looks like this. And 26 will be pointing down, and 66 will be pointing, we'll all come up with the thing. But you see what happened. We got an extra node out of it. Okay, and actually I guess to be accurate with my everything, what's going to happen is 20, let's see. Fortunately, it's hard to redo to get this tree. So I'm just going to do the top part. So what's going to happen is you'll end up with 51. Okay, and it's going to go to 2 children that have 26 and 41, and the other one is going to have 66 and 87. So 87 is going to point to here. This one's going to point to here. Sorry, still getting this wrong. Yep. It's not right.
Point to the right half of the middle.
Yeah, I'm just like, I've gotten myself confused, so I have to back up for a moment. So 26 is going to be pointing way over here. And then the next one should be pointing here. Then the 41 is going to be pointing to a new split node. So this node right here split in 2 and became 44 and 48. And this node also split with 51 being promoted. So the 41 is coming into this new node, and then the 66 is coming into that node, then this and this. Okay, I know that's somewhat confusing, but I can't really easily modify this diagram. Okay, but hopefully you have the idea of what's happening. And in this case, the root, as you can see, only has 2 children. It's the only one that's not more than half full. So questions about this? Yes.
Just to clarify, they each have a left and right pointer, right? So there's one left, or one right will point to the other's left.
Yes, in effect, so for example, here, 70, with 78 and 72, 72's right pointer is the same as 78's left pointer. So I was just using left and right for each individual node, but they each, in effect, 2 keys share a pointer. For one it's the right, and for the other it's the left child. Other questions? Okay. I'm not going to worry about deletion, so don't worry about deletion for this course, okay? Just worry about insertion. Deletion generally, well, is there? Okay, if there's deletion on the homework, okay. There may be, so then I will go over it. I was just noticing the time, but I will go over deletion in that case. Okay, it's not that hard. Okay, so deletion, okay, with deletion, if you're going to delete something, you're okay, so deletion, if the leaf after deletion still contains L divided by 2 or more tuples, you're done. Okay, so if I'm deleting, say, 46, that's okay because L is 5 and L divided by 2, upper bound is 3. So if I delete 46, there's still 3 keys, or tuples rather, in that leaf. So the interesting case for deletion is what happens when the number of tuples falls below L divided by 2. So 46 is not particularly interesting. What happens instead if I end up deleting 98? Well, that's not interesting either. Let's say I delete 90. Now, that would bring that tuple below half full. So the first thing we do is a strategy you suggested, which is we move a tuple if we can. So we look at our neighbors and see if they can spare a tuple, which in this case, can this leaf spare a tuple? No. What about this one? Yes. So what we're going to do is move the smallest tuple from the right leaf, in this case, over to here. If it had been the left tuple, what would we, if there was the left block, which tuple do you think we would move? The last one. So it just depends whether it's the left or the right one that we're borrowing from. Stealing from would be a better word. So now 92 would move over. If we move 92 over, what else do we have to do? Change the key up here. It needs to change to the next key in the leaf that lost the tuple. So that's pretty easy too. If we can borrow, so if, let me go now for a moment to here. So deletion. So we already did step 1. If more than L divided by 2, tuples remain, do nothing. If fewer than L divided by 2 tuples, A, if we can borrow from a neighbor, if we can borrow a tuple from a neighbor, then move the tuple to the leaf with the deleted tuple and update the parent of the leaf which lost the tuple. Okay, actually, if more than L divided by 2 tuples remain, do nothing is not quite right. You might do nothing except possibly update the parent. Okay, so if in this example, right here, I deleted 46. Let's say instead I had something where I deleted 72 right here. Okay, 72 is, if I delete it, there's still enough tuples in the leaf, but 72 is gone, so I'd have to change the parent to be 73. So in fact, that's even if there is enough tuples remaining, you may have to update the parent. Okay, if there's fewer than L divided by 2 tuples, if we can borrow a tuple from a neighbor, move the tuple to the leaf with the deleted tuple, and I should say update both parents appropriately. So both parents might have to be updated. Both parents as appropriate. Okay, so the interesting case is B, and in B, we're going to end up with we can't borrow. We can't borrow. In that case, we merge with a neighbor. Okay? And if possible, you should merge with the left neighbor. So if possible, for this course, merge with the left neighbor. Of course, if you're the leftmost node, you'd have to merge with the right neighbor. So just going back to here, in general, you will have a left neighbor, like this one, this one, this one, this one, all have left neighbors they could merge with, but if you're the leftmost one, you'd have to merge right. Okay, so, yes?
In the 72 example, why would you have to change the key in the parent? The 72
Okay.
is not viable.
If I delete 72,
Right.
okay, it's no longer in the, there's no key that's 72 in the tree anymore. So you're right that 72 is still viable, except that the key has to be one that exists. 72, when you delete 72, it no longer exists.
Even for a B plus tree?
Yep. So you need to update it so that it's 73. Yep. So you need to make sure you update the parent. At least for this course, I'm going to make you update it. I think there are possible, you have to be worried then what happens if you have a non-existent key up here and you get insertions and deletions. I think at some point you could end up with issues. So I think it's important that this key in the interior node always represent a real key in the leaf. Okay? Yes?
If the left and right neighbor can both spare the tuple, do you steal from the left first?
For this course, yes. So for this course, if you can steal from both left and right. So I would say when borrowing, first look left, then look right. So that means if you can find something in the left, take from the left. Yes.
So this might be a difficult question, but suppose we just had the leaf nodes here, we didn't have any of the internal structure information.
Mm-hmm.
Is there a unique internal structure that corresponds to a certain set of leaves?
No, because it all depends on insertion. The order in which you insert things can lead to different trees. So actually, if you want to experiment, there is a good website. So I should have mentioned, I was going to mention it then, but there's a, right at the bottom of the lecture notes, there's a site, B+Tree visualization, and you can actually show that by inserting nodes in different order, you will end up with different tree structures.
But for a given that the leaves are structured a certain way.
No, I'm pretty confident that you could still have different,
Internal structure.
yes. Mhm. I'm almost positive I could come up with that. So we're still now, we can't borrow a tuple, so we're merging. This is our last case. So let's see, I think they're going to delete 90. Okay, so here what they're going to do is delete 99. Okay, so we look left, that's the only place we can look, and there's no way we can borrow. So in that case, what we have to do is merge these two nodes. So we merge them together, getting rid of this one. When we do that, we're going to lose a key. The key that pointed to the deleted block is going to go away. Okay? That's not a problem if this would not be a problem if what? We could stop here if, so the key that points to the deleted node is removed from the parent. Okay, so that's step 2. We merge and delete a node. The key that points to the deleted node is removed from the parent. We are done if how many keys, if the number of keys in the parent is greater than the upper bound of m divided by 2. Actually, I think it's the number of children. I take it back, the number of children. But that's not the case here. Okay, the number of children is less than. So, what we're going to do is the same thing. We're going to see if we can borrow. Can we borrow from here? And the answer now is yes, we can. We can actually move 83 over. Because if we do that, we'll lose the key here. But it will still have 3 children, which is enough. And we will now have 3 children over here. So in fact, we can add 83 as a key, and we are good. So it's the same strategy that if we are done if the number of children in the parent is greater than m divided by 2. If not, then employ the same borrow, or merge strategy. With parent. So you first try to borrow. If that doesn't work, you merge. And you could, in an extreme situation, end up reducing the height of the tree by 1. That's not going to happen anytime soon here because this node is full. But if we were deleting from that tree I created with 51, if you ended up having to merge its 2 children, then clearly the merge should mean that the 2 children become the new root. Yes?
Supposed to be greater than or equal to m over 2, or just greater than?
It can be greater than or equal to. Thank you. As long as it's half full or better. Okay, so that's the deletion strategy. Any questions? I know this may take some time to figure out. That is right. So when you do it and move it over, you're going to have to update that particular. It's the same thing. When you do the borrow and merge, you'll have to update the parent. So what I have here, if you're putting this stuff, 1, 2, and 3 here are in your notes, it goes under B. So we can't borrow a tuple, we merge with a neighbor. So in your notes, 1, 2, and 3 go under B. Okay, so 1, 2, and 3 here go under B. Okay, and turns out that if we force things to be full, then the number of levels is less than or equal to roughly log m divided by 2 of n. So this is an m divided by 2 of n. N is the number of tuples. So by forcing your leaf nodes and interior nodes to be greater than, at least half full, That's why you do it, so that you can ensure this condition right here. You know that at every interior node has to be at least half full. So in the worst case, this is the number of levels, and the number of levels equals the number of disk accesses, the maximal. No, because of caching. So sometimes, almost always the root will be cached. So it's, remember, on a test, answer with the maximum number. In practice, usually the root is cached. Usually some of the first level blocks are cached. So usually it's going to be less than that. But this is the, if I ask on a test, what is the maximum number of disk accesses, this is your answer. Should be your answer. Okay. So that's going to be much better than log 2 of n. And I'm going to leave most of the implementation for extendable hashing until next time. I'm just going to quickly motivate what happens with extendable hashing. So it turns out that log 2 of n is good, or log m divided by 2 of n is good, but you can still get multiple level trees. So, some clever people said, is it in essence possible to ever make it so that you have, in effect, a tree where it has at most 2 levels, where the root is in some sense enormous, and then each node in the root points to a leaf? Okay, that would be really neat. So you could try to do that with a B+ tree by making M enormous, but in practice you can't because you're limited by the block size. So you can do it because this looks a lot like a hash table. Okay? And with separate chaining in effect. So what we're going to end up doing, extendable hashing is going to be basically based on the notion of separate chaining. An enormous array, and each element of the array pointing to a block, the block containing all records where the key hashes to that particular entry in the hash table. And you might say, well, why can't we just use separate chaining by itself? And it turns out that separate chaining doesn't quite work because you can end up with, if you have too many records going into one bucket, then you might end up with, if like each leaf can hold 50 records, but too many records come into here, so it needs to store, say, 75, the solution in separate chaining is fine. You just have a big linked list with 75 records. The solution here would be to have a linked list of blocks, but now you no longer have a guarantee of 2 disk accesses. So separate chaining doesn't quite work with disk accesses. It can't guarantee only 2 disk accesses. So some clever people came up with extendable hashing, which we will talk about next time, and which I guarantee will not take the entire class period because it's much simpler. And we'll spend the rest of the time reviewing. But extendable hashing can guarantee that we always have at most 2 disk accesses. So we'll talk about that next time. I don't believe extendable hashing is on the homework. Even if it is, you'll be able to solve it after our class on Thursday.